All right, so we're back and we're at the bottom of our stages of problem solving, and our last phase is to evaluate the solutions that we generate, decide what a good solution might be to the problem. Levine said that we go through a series of hypothesis tests. I was kind of encouraging you during the Petals on a Rose demonstration to generate hypotheses and see if the next dice roll clarifies whether your hypothesis is supported or refuted, right? What Levine says is that we go through like a global focusing strategy where we can maybe keep track of more than one hypothesis at a time as we're trying out, like, is this working? Is that one working? Which one is the best strategy, right? As we go along, we start rejecting those that aren't consistent with the feedback that we're getting. So I'm going to give you an example of another kind of problem. And this is one that, definitely you have to do live, but I'm going to kind of set up the problem for you and you can maybe test it out on your friends and family for fun. And this one's called the green glass door. So I'll give you some examples of the green glass door and then I'll ultimately tell you the solution. But what I want you to do is listen to what I'm saying and test out mental hypotheses. Like think about what might be the solution to the problem I'm presenting. So what you're looking for is what can go through the green glass door and what can't. So I can say that puppies can go through the green glass door, but dogs can't. Kittens can go through the green glass door, but cats can't. Books can go through the green glass door, but a computer can't. Let's see, what else? Wool can go through the green glass door, but polyester can't. What else is a good example? A hook can go through the green glass door, but a knife can't. A button can go through the green glass door, but a switch cannot. Goop goop can go through the green glass door, but slime cannot. Oh, those are kind of like analogous things. Goop can and slime cannot. Let's see. That's probably enough to get you started on what might be going on. And then what I like to do in real class when you're face to face and I can hear you is ask you if you think you're getting it, to generate something that you think would fit the criteria that allows some things to make it through the green glass door and other things not. A big hint is the title of the game, Green Glass Door. What do those words have in common? Green glass door. So something that's green can make it through the green glass door, but something that's blue can't. So one thing that those words all have in common is that they have double letters. Green has two E's, glass has two S's, door has two O's. And so you might have been testing out hypotheses like if it has an O or it has a vowel or something like that. You might have been trying something having to do with letters. You might have been thinking of the objects, right? Because what I tried to do was give you analogous objects, puppies and dogs, books and computers. So I tried to give you analogous objects to maybe throw you off a little bit, right? So you wouldn't notice right off that it's just strictly having duplicate letters in the word. So now that you know the rule, where it's fun is to like, ooh, we have Thanksgiving coming up. Oh, I don't know when you're going to be listening to this. It might be after Thanksgiving. It's before Thanksgiving when I'm recording it. So maybe a family gathering would be a fun time to introduce the green glass door and see if people can solve the problem of what kinds of things can go through the green glass door and what kinds of things can't. And generally what you see is that people do seem to be like holding on to different hypotheses and then rejecting them as needed, right? So what Levine thinks is happening is that we select a working hypothesis from the pool of existing hypotheses. And then if the feedback is consistent with the hypothesis, then we keep it until the next trial, right? Until the next time we face this problem. If the feedback is inconsistent with the hypothesis, then we go ahead and choose another working hypothesis that is either so far consistent with the feedback, or maybe I have to generate a new one because everything I've come up with has been blown out of the water. The first time I played the green glass door, my daughter had brought it home from Girl Scout camp, and I could not. I could not. And she kept saying green glass door, and she's like, I'm giving you a hint with the name. And I'm like, I don't know what you're talking about. So I was like throwing out hypotheses left and right. I was having nothing but trouble trying to solve it. So, that's what I think sometimes you have to even make up some new ones, right? So Levine's theory is a pretty good theory explaining how we evaluate the solutions that we've generated for problems. The evidence that we have for this approach is that, adults are generally pretty intelligent, right? And they certainly look intelligent compared to children who have less sophisticated hypothesis testing capabilities, right? So the fact that adults are intelligent, and especially compared to children, that's support for Levine's theory. Another piece of evidence for Levine's theory comes from tests where the tasks are relatively simple, like trying to figure out what can go through the green glass door. So if it's a relatively simple problem, you'll see this kind of hypothesis testing. Evidence against it is that people have limited memory skills. And so the idea of being able to hold a pool of existing hypotheses, I mean, there's a game show called America Says, and they'll put 7 prompts up on the screen, and they each have the first letter and then a blank. And the blank is designed to be drawn to kind of give an impression how long the word is. And you're supposed to come up with 7 words that America said in response to some prompt. And at the beginning of the 7, when they're all blank, I'll go through and I'll see the different letters and I'll have my ideas in mind and I'll say them out loud. I'll even say out loud what I think the solution to those different blanks are. And then the players will start to say words and start filling some blanks and saying other words that are wrong and things like that. And I'll forget some of the solutions I had generated like 10 seconds ago, right? I couldn't hold it in my memory long enough with all this other competing information coming in. I'm not sure that our memory skills are up to the task of holding multiple hypotheses simultaneously, testing them and rejecting them and pulling new ones out. And then the other evidence against it is that this doesn't seem to be the strategy that we use when we have more complex problems, like life problems, problems that are not as clear cut as the kind that we would introduce in, experimental situations. Even in experimental situations, we can generate more complex problems that people tend to not seem to display this kind of approach. But if you play the green glass door with your family, you might see them displaying Levine's theory of hypothesis testing. All right. The next topic I wanted to address is that, there are some obstacles that stand in the way of us being the most effective problem solvers that we could be. One obstacle is what we call persistence of set. If you recall, the word set refers to expectation. So if you have a pre-existing expectation for how this problem's going to go, it can be very difficult to get rid of that expectation, even in the face of information that lets you know that that expectation is faulty. Okay, let's see if this will launch. Yay. So this is called the Tower of Hanoi problem. And in this problem, I'm just going to do the simplest one, which is the 3 discs. In this problem, your job is to move one disc at a time to another peg so that you can ultimately move the entire stack to, I don't know if it tells us what, I'm going to say we want to get over to Tower 3 is our goal. So you want to do that in as few moves as you possibly can. So if I'm going to do 3 discs, and I want to end up on Tower 3, I'm probably going to go, you can never put a bigger one on top of a smaller one. So I'm going to go like this. And I'm going to move my little discs over. I got it in 7 moves, so I met the criterion, right? So that worked for 3 discs. I'm going to do 4 discs. Okay. So on the last one, I moved disc 1 to Tower 2 first. We're still trying to get to Tower 3. if I move disk 1, I'm going to try and make the moves mentally. If I make disk 1 go here, and then I make disk 2 go over here, and then I put disk 1 on top of it, and then I put disk 3 on tower 2, then I move disk 1 over here, 2 over here, 1 over there, then I move the big one. I don't know if I'm going to make it in 15 moves. I'm going to try, let's see. I prepped it because I don't want to be told I'm wrong. Isn't it stupid that it's punishing to be told by a machine that you did it wrong? Kind of dumb, but it is. I don't like to be told I'm wrong. All right, so I did that in 7 moves just like I did last time. Okay, now I'm going to go here, which is, see, this is a slightly different approach than you do when it's 3, a very different approach, right? I think I'm going to make it in 15. Yay, I did it. Okay, now I have to tell you, this is not my first time at the Tower of Hanoi rodeo, and so yeah, I knew that was going to work. Here's where it gets crazy. Okay, so it says it'll take 15 moves to do 4 discs. It's going to take 31 moves to do 5 discs, 63 moves to do 6 discs, 127 moves to do 7 discs, and 255 moves to do 8 discs. Once you're successful with 3 discs, 4 discs, I'll give you the foreshadowing that 5 discs works. 6 discs work very similar to what I've shown you so far. The critical dividing point is when you get to 7 discs. Suddenly, nothing that you've been doing before is going to pertain to solving the 7 disc problem. But it's really hard for people to abandon the strategy that has been working on the previous problems. And so they'll persist. Now, let me give you a more concrete example here in this chart. This is called, very creatively, the 3 jug problem. And in this problem, the rule is that you have to fill the jug all the way to the top in order to be sure that you're measuring out the amount of water that you're trying to measure. So in problem 1, we're asked to measure out a total of 100 units of water, and jug A can hold 21, jug B can hold 127, and jug C can hold 3. So you need to get to 100 units of water. So it doesn't take a little long for people to figure out with this problem that ultimately the solution is to fill B all the way up, dump into jug A, so that's going to be taking 21 units out of jug B, and then you're going to pour into C, empty C, pour into C again, and that's going to leave behind 100 units. And here's the little like algebraic equation, right? So you're going to do B minus A minus 2 times C. Right? So that's the procedure. And you go through and you say, okay, that's actually going to work again, right? So you're going to fill B, dump into A, dump into C, dump into C again, and that's going to leave 22. And so that works, right? And you realize, hey, wait, it's working for all of these. Then you get to trial 6. And on trial 6, that same strategy will work. You can do 49 minus 23 minus 6, and you'll end up with 20. Or we're going for 20. What if we just went ahead and filled A, dumped into C, and have 20 left in A? But what you'll notice is that people will display persistence of set. And on the critical trial number 6, they'll fill B, dump into A, dump into C twice. They'll go the same exact route. Trial 7 is an interesting twist because in trial 7, you could potentially go the same direction that you had on trials 1 through 5, but this one's even a different solution from trial 6. If you were to fill A and dump it into B, and fill C and dump it into B, you'll have 18 units. So it's even a different solution than trial 6. People, once they've figured out trial 6, are much freer for noticing what the pattern is for trial 7. If you can break your set, you now are going to display greater cognitive flexibility than even at the beginning of the game. But it's really hard to break that persistent set. You know, you do tend to do the same thing over and over again. All right, I think I've been talking for a while, so I'm going to stop and we'll talk about functional fixedness in the next video.